Hello, we are going to talk about kinematic constraints of mobile robots. Fundamental assumptions. First, the wheel plane remains vertical at all times. This ensures the wheel's rotation is restricted. It doesn't cause unwanted tilting or deformation. Second, single point of contact between each wheel and the ground. This allows us to treat this interaction as rolling motion. Okay, or rolling condition. The velocity at contact point is zero. In other words, there is no sliding, slipping, and no lateral motion. So it causes non-holonomic constraints. Okay, motion occurs on a horizontal plane. Reduce the degrees of freedom. So we are going to work in a 2D motion. Also, the chassis is rigid, so there is no internal deformation or vibrations between wheels. The steering axes are orthogonal to the surface, so the steering is purely rotational. And finally, a free wheel rotation, so there is no torque resistance and no rolling friction.
In this slide, we can see the Pixar standard wheel, which is one of the simple wheel types used in mobile robots application, because it cannot slide sideways, so it's fully constrained in lateral direction. These two equations describe the motion as constraint. The first rolling constraint, which ensures that the wheel rolls without slipping along its direction of movement, and the second one is the sliding constraint, which prevents any sideways direction.
For the static standard wheel, the equation showed two main constraints. The pure rolling constraint includes terms with sin and cosine of alpha plus beta, and it ensures the wheels move without slipping in the direction it is facing. The sliding constraint prevents motion to the side of the wheel. Because of the angle beta, the wheel can rotate around the vertical axis, allowing the robot to change its direction of movement. This increase maneuverability while keeping the motion physical consistent with the rolling condition. For the caster wheel, the equations are similar but include an additional term of offset distance d. This offset means the vertical axis of rotation does not go through the contact point with the ground. As a result, when the robot moves, the caster automatically rotates to align itself with the direction of motion. The rolling constraint still makes sure there is no slip, but the sliding constraint now depends on both the steering angle beta and the distance d.
We have the differential rate robot example in this slide that show a robot with two standard wheels fixes, the left and right. The point P is the center of rotation of the chassis. Since the wheels have no steering, they can only move forward and backward, introducing no slipping constraint that eliminates any lateral movement. That's the reason that we apply the kinematic constraint to the model. So we can see the equation shown here apply the kinematic constraint. Because both wheels are parallel, only one independent constraint remains, which links to the robot linear angular velocity to the angular speeds of the wheels. In simple terms, this matrix means that the linear velocity is average of both wheel velocity. The angular velocity is depending on their difference. So this explains how the robot can move straight, turn, or spin in place depending how. So this is a summary of the wheel constraint that we can see in the course, the reference that we obtained the information. Thank you.